Okay, welcome everyone. As usual, we'll get started with this problem in a few minutes. But let's start out with class announcements. So about problem set 2. Problem set 2 is due again 1 week from today at 11:59 p.m. Montreal time. A few clarifications. On problem 4 in particular, there are a couple of questions about whether one should prove that there is exactly one person or at least one person who knows all the other people. It should be at least one person. You don't have to prove it is exactly one. In fact, in general, it is not exactly one. And also the words knows all the other people probably should have been is friends with all the other people. Sorry about that. Being friends with somebody is not the same as knowing them. There will be the next office hours on Monday right after class. So I encourage everyone to come and chat about the problems. If you have specific questions or if you're just confused about things, want to listen, want to ask just how to think about the problems, come to office hours. Also post in the Slack. Find collaborators by messaging in the problem set 2 channel. Everyone should be in that channel. If you want to chat with a collaborator, find a collaborator who wants to work on a particular problem, that's a great place to find one. Highly encourage it. Congrats to anyone who was submitting to the iClear conference today on being done with it, for better or for worse. I know that I am a bit tired for that reason too. Okay, are there any questions? Can we get complete solutions for problem set 1? Yes, there will be complete solutions for problem set 1. Score statistics, I'm not sure yet. More questions? Great. So today we'll be starting out calculus. And so basically today it will be a really fast look at single variable calculus. Not all of what one would cover in a single variable calculus course, but some amount of it, and just some things that I think are important to know about derivatives, and if we get to it, integrals, and the ways one would go about mathematically proving some simple facts about derivatives in particular. Really trying to get mathematical underpinnings. I know some of you, many of you may have seen these results, but just looking at them from a more mathy perspective can be useful in terms of understanding how to think about things. And if you have to derive something yourself, it's really helpful to know what everything is built off of. So with all that said, let's dive in. And also with the caveat that I'm not going to be really rigorous about calculus. I'm going to try to help you to understand why all of these things are true. Technically, we'd have to be doing some more rigorous stuff in order to actually define all of these things that I'm going to be defining. But this is fairly mathy. It's not as super mathy as you could go if you really want. Okay, so let's start out with what derivatives are. The derivative of a function is defined as the limit. The function is f of x. The derivative is often denoted f prime of x. It is another function of x, which is the limit as you take some value h going to 0 of f of x plus h minus f of x divided by h. So this is a definition of a new function based upon f of x. And importantly, there's that weird limit in there. So let's take a look at what that means. And just another way to write this is d by dx of f of x. So these are all ways to write the derivative of f of x, f prime or d by dx. Great. So how should one think about this whole limit thing? Well, what f of x plus h minus f of x over h is it's a slope of a graph. And so if you look at this curve of the graph f of x, then f of x plus h minus f of x over h is just the slope of this line. That's how a slope is defined. Now, if you make h be very small, you're essentially moving this point, x plus h, f of x plus h, all the way to this point. And so what you have is you have a slope. You know, this long slope is becoming closer to the slope for 2 points very close to here. So it's basically the instantaneous slope or the tangent to the curve at this point xy. So that's what the derivative is. It's the instantaneous slope of a curve. So if the curve is going up very steeply, then the slope will be very high in magnitude. If the curve is very flat, then the slope will be close to 0. And this is just generally telling you, it's an evaluation of the instantaneous slope of a curve. In fact, it's the definition of the instantaneous slope of a curve. Now, this limit, I'm not really going into what a limit is, but limits are not something that you can always do. Just to make you a little bit aware of why these are tricky things. Limits don't always work. For example, if you have the function y as absolute value of x, that does not actually, it has these instantaneous slopes, derivatives at all of these points, but if you try to compute the slope at this point, well, it has this bend. It's a sudden bend, and there isn't actually a slope there. Or more properly, this limit actually is different depending upon whether h is positive or negative, essentially. Because if you are taking the limit coming from this direction, then all the slopes here are 1. If you're taking the limit coming from this direction, all the slopes are -1. So from this direction, if h is positive, you have +1. From this direction, if h is negative, you have -1 as the derivative. So since +1 and -1 are not the same, the derivative is not defined at that one point for the absolute value function. And in general, the way that limits work is you have to have the limit converge. And I'm not exactly going to go into what convergence of a limit means, but you have to have the limit converge from both sides in this case. So h going to 0 from both above and below. Here's another example of a function that doesn't have a derivative. This is the floor function, which is just the greatest integer that is smaller than or equal to x. So for example, floor of 2.5 is 2, floor of 2.8 is 2, floor of 2 itself is 2, but floor of 1.9999 is 1. And so there are these discontinuities. And because of those discontinuities, the function does not have derivatives at these at integers. Okay. So not every function has a derivative. Another way to say that a function has a derivative is to say it's differentiable. But a lot of functions we will be looking at do have derivatives, and if you combine different differentiable functions, you're also going to get differentiable functions if you're taking products or sums or powers or compositions or other things. So in general, a lot of the functions you're going to see are differentiable. There's a question about partial differentiation. We're not going to be talking about multivariable derivatives in this particular class, but we'll be getting to them a bit later. And yes, if you're looking for the LaTeX command for doing a partial derivative, that is \partial, yes. Is it the same thing as a function being well-defined to say that it has a derivative? No, there are different things with derivatives. You can say that the first thing is a function is continuous. It doesn't have any jumps in it. The next thing is it's differentiable. Then you could say that it has 2 derivatives, or the derivative is continuous, and it has 2 derivatives, 3 derivatives, 4 derivatives, and so on. There are functions that have 3 derivatives. You can take the derivative again and again, but then at that point, it suddenly stops becoming differentiable. So there are, and you can look up the class of C infinity functions, which are functions that are well behaved for any number of derivatives, basically. Okay. I mean, you don't have to worry about that, really. We're just going to be looking at functions that are differentiable. And it'll be pretty obvious when a function isn't differentiable generally. So some simple properties of derivatives to start us out. Addition. The derivative of the sum of 2 things is just the sum of the derivatives. cool. So let's see why that's true. Well, the derivative is defined as the limit of the difference between the function of x plus h and the function at x, all divided by h. So let's just plug that into f of x plus g of x, and we get this. We can break that into two terms, one of which is just the derivative of f, and the other of which is just the derivative of g. Okay, so it's literally just dividing this big sum into two things which are the derivatives of the individual functions. So that's the proof. Similarly, pretty simple, if you want to multiply a function by a constant, what's the derivative of that? Well, it's just going to be, the constant moves outside the derivative, so it's going to be constant times the derivative of the original function. So why is that true? Well, in the same way, we just write it down. The derivative of constant times the function is just the limit of this, where instead of f, you have cf. But you can move the c outside just because of multiplying by constants. And then you have c times the derivative. Okay. So those are some simple properties. Let's take a look at some actual derivatives of real life functions. So what's the derivative of x to the n for integers n greater than or equal to 1? Whoops. How would we do this? And write the limit definition. Yep, there's going to be an x plus h to the n, and there's going to be an x to the n. What can we do? Yeah, we have binomial expansion here. X plus h to the n, we can use the binomial theorem. And that is going to expand out to this horribly long thing, minus x to the n. So one of the terms cancels, that's good. The first term cancels. But then we have all these other terms, and we have all these horrible binomial coefficients. I divide it out by h, because I could do that. So this is really ugly. There are tons of terms. How do we make it simpler? Or is that just the derivative of x to the n, some nasty thing? Okay, great. So here's the thing with limits. The reason why we could, when you see a limit of something going to 0, the first thing you should try to do is just literally set that thing equal to 0. So if you set the thing equal to 0 in just the definition of the derivative, you would have function of x. This is the definition of derivative. Function of x minus function of x over 0. So it's 0 over 0. The reason why the derivative is a bit more sophisticated than just literally plugging in h equals 0 is because if you plug in h equals 0, you get something that's indeterminate. 0 over 0 could be anything. It could be 0, but it also could be 17. Now, if you plug in 0 to something where there's a limit of h going to 0, and you don't get basically 0 over 0, then you're fine. That's just the answer, right? So you plug in h equals 0 here, all these terms just become 0. And then the only thing that you have left is this first term. So all the terms except the first are divisible by h, so they're going to go to 0. So the answer is just n choose 1, or n times x to the n minus 1. So how do we use that to take derivatives of polynomials? Well, since we know that the derivative of a sum is the sum of the derivatives, and the derivative of a constant multiple of something is the constant multiple of the derivative, we can take the derivative of an entire polynomial. Or I'm going to start using the word differentiate. Differentiate means to take the derivative of. Do not use the term derive or derivate. Those are not actually words for taking the derivative of something. Use the term differentiate or take the derivative of. Okay, so here's an example. Let's differentiate this polynomial. 5x to the fourth minus 2x cubed plus 1. So we can split it first into each individual term. Good. We can move outside the constants. The 5 comes outside, 2 likewise. And now we have these monomials, x to the fourth, x to the third, and 1. Now how do we deal with those? Well, x to the fourth, we know from our previous result back here, the derivative of x to the n is n times x to the n minus 1. So plugging in n equals 4, we're going to have 4x cubed, and we're going to have 3x squared here, likewise for x cubed. And then for 1, what's the derivative of just 1? Well, in general, we'll find that the derivative of any constant, and it's pretty easy to see that the derivative of any constant is going to be 0. Now, why is that? Well, if you just graph it, the slope of a constant is just 0. Or, more obviously, if you take the definition of the derivative, if you have a constant, it's just like constant minus constant. So that's just 0. Okay. So the derivative of any constant is 0. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. And so we get this as the result. So in general, if we take the derivative of a polynomial, we're going to get a polynomial of 1 lower degree. The first degree is going to go down, and all the other terms are going to go down by 1. Okay. Now, let's derive what's called the product rule. I really don't like it when math is taught by rules, because this is not really a rule. It's just logic. If you go through it, it'll be just pretty self-evident from the definition of derivative. So let's do that. What is the derivative of the product of two things? Start out by writing the definition of the derivative. What can we do? How can we make this something tractable? And yes, there is a nice formula for it. How can we prove it? Why is that formula true? Okay, so there's a good suggestion. There is also a suggestion of L'Hopital's rule. I don't think we could take L'Hopital's rule very clearly here because we haven't seen L'Hopital's rule yet, but I don't think it'll be applicable in this situation. Also, we don't need something that heavy. So yeah, the suggestion was to add another term. So we can add and subtract. This is generally like a really awesome thing to do in certain situations. In order to do something with an expression, you can add something and then subtract it as well. So all I've done here is added function of x times, f of x times g of x plus h over h. So I've added it here, and I've taken it away here. These four terms are really actually just these same two terms. So what can I do now? Why was this a good idea? What's the first part here? Yeah, so the first part is going to be, we can just pull out the g of x plus h, and we have the limit of g plus x plus, limit of g of x plus h times, and then that's f of x plus h minus f of x over h. So f prime of x. So that's the derivative of f times this. And then likewise, this is just the derivative of g times f. Okay. Now, again, this is a limit where we can just set h equal to 0. So let's just set h equal to 0. We have f prime of x, g of x, plus g prime of x, f of x. And that is the product rule. If we try to calculate the derivative of a product, we just calculate the product of the derivative of one and the original thing, and the derivative of the other and the original thing. Just sum those two products. Okay. Here's an example. If we take the derivative of this product of x to the m and x to the n, we have the derivative of the first times the second without taking the derivative, plus the derivative of the second times the first. Remember, mx to the m minus 1 is just the derivative of x to the m, and nx to the n minus 1 is just the derivative of x to the n. But this nicely simplifies to m plus n times x to the m plus n minus 1, which is, fortunately, the same thing we would have gotten if we just taken the derivative of x to the m plus n directly. So math works out. Always makes me just a little bit happy when something that should work out, you can prove it in two different ways. That's good. How could we set h in the denominator to 0? Well, we didn't actually set h in the denominator to 0. It's just the definition of derivative up here is f prime of x equals f of x plus h minus f of x over h. So we just pulled out g of x plus h, and then everything else, including the h in the denominator, was the definition of f prime of x. Good question. Okay. Please keep asking questions. Let us move on. So I'm not going to go into the full quotient rule, but in order to get a sense of it, what is the derivative of 1 over x to the n? So yes, you can see it as x to the negative n. However, what we proved before was only true for positive exponents n. We use the binomial theorem, which is true but more complicated if you're looking for negative exponents. If you're curious, look up the binomial theorem for things that aren't positive integers. It's pretty cool. So we can't do that. We can do something else. We can do something cool. So suppose this derivative exists and it's some function f of x. Let's use the product rule. The derivative of the product of 1 over x to the n and x to the n is going to be, we can just apply the product rule. So what's the derivative of the first one? Well, it's f of x times, and then the second one, plus the first one times the derivative of the second one. This is just the product rule if I apply it to the product of this and this. We know that the thing on the left is just the derivative of 1, which is 0. So that means the thing on the right also has to be equal to 0. So f of x times x to the n plus this other thing is equal to 0. If we move things around, we get f of x times x to the n is equal to just minus n over x. And so then if we divide by x to the n, we get f of x equals negative n over x to the n plus 1. And this is great. This makes us really happy because the derivative of x to the m was mx to the m minus 1. But that was true for positive integers m. But here, we're basically seeing that it's true for negative integers too. Because for a negative integer, if we write this as x to the negative n, then we're going to get negative n times x to the negative n minus 1, which is the same as negative n over x to the n minus 1. So this is, in a sense, a proof that this holds not just for positive integers m, but also for negative integers m. And in general, it's actually true not just for integers, it's true for all real m, but we won't prove that. Any questions? There's a question about x to the negative n minus 2. I'm not sure what the question is exactly. X to the negative n minus 2, if you took the derivative of that, you would get negative n, you would get minus n minus 2 times x to the negative n minus 3. If that didn't answer your question, then please feel free to message me separately or private message me here in Zoom. Is there a geometric intuition for this? It's a really good question. I don't really have a geometric intuition because I don't have a clear geometric intuition for the graphs of polynomials. But there is yeah, I don't have a good geometric intuition for it. I'm sorry. Okay. Now let's move on to another rule that you might have learned in calculus class, the chain rule. So let's prove that too. What is the derivative of g of f of x? Let's again go into the definition of the derivative. Now what can we do? Why is this true? It's just substituting variables. What do you think we should substitute? This is tricky. This is not at all obvious. I just want you to think about it, basically. So we can substitute y equals f of x. And that might work, but there's sort of there's a cute way that I'm going to suggest doing it. Y equals f of x is not a bad idea here. It's just that it's a little bit difficult to think in terms of. I mean, yes, you could. That is absolutely a way. That is absolutely a way that you could do it. Let's do it a slightly different way. Yeah, this is a suggestion of looking at f of x plus h minus f of x. So let's set j equal to this. Then if we take what we had before, we can rewrite it as just the limit as j goes to 0, because we know that this is going to go to 0 as h goes to 0. So we can, the limit is the same limit, just h goes to 0 or j goes to 0. We can write it as g of f plus x, f of x plus j minus g of f of x. This really looks like a derivative of g. Only problem is we're not dividing by j, we're dividing by h. So how can we fix that? Well, what we could do is we could Just like we can add something and subtract it, we can divide by something and then multiply by it. So we can say, okay, we're going to just divide this by j. So we get the derivative of g, or something that looks like the derivative of g, and then we're going to have j over h. But if we go back to what j was, well, j is just equal to f of x plus h minus f of x. So here we have the derivative of g applied at f of x, and here we have the derivative of f. So this is the derivative of g at f of x times the derivative of f at x. So I mean, these are definitely useful rules to memorize, but it's always useful when you're memorizing something to have an idea of why this is true. And there are different explanations for the chain rule. Like there are many different intuitive explanations, and this is just one of them. Okay. Let's see it. Let's just go back for a moment. We assume that j is approximately h. We know we aren't actually assuming that j is approximately h. That's the cool thing. So the point is that when h is going to 0, j is also going to 0. Basically, a limit just means you're taking h very small. But if you're taking h very small, you're also taking j very small. It doesn't matter exactly how small you are, just as long as, since h is going to 0, exactly when h is going to 0, j is also going to 0. The situation when j gets close to 0 is the same as the situation when h is getting close to 0. In general, you could think of these limits like, what happens when h is really small? Well, so when h is really small, j is really small. So that means this is a good approximation of the derivative of g. And when h is really small, this is a good approximation of the derivative of f. It's as simple as that. When h is really small, j is really small, so both of these are good approximations. And if you take the limit, those good approximations become exact. Okay, so there are a couple of different questions. First, could we write both limits out? Yeah, I sort of glossed over this a bit. It's probably, you could say that, like, what I was saying is fairly rigorous. Basically saying when h is very close to 0, this is going to be an approximation to what we want. When h is very close to 0, j is also very close to 0. So this is going to be the same approximation to what we want. I'm not substituting h for j for h. The equation is just doing it is, this is just literally rewriting f of x plus h as f of x plus j. That's just a substitution. Over here, this is just because when h is going to 0, yeah, exactly. J equals 0 exactly when h equals 0, or at least in that small little area. And h equals 0, and when h is close to 0, j is close to 0. The limit is just saying this thing is a good approximation when j is close to 0. It's a good approximation when either h or j is close to 0. Yeah, so really good question. I was just being sloppy here. You should probably write lim j goes to 0, lim h goes to 0 here. But since they're the same limit, basically. Now, these are really good questions. And I'm sorry also that sometimes I'm not going into as much of the detail. Partly it's for time reasons. Partly it's because it's actually really annoying having to try to fit an entire proof or the idea for a proof on a single slide. And it's really confusing if you skip slides because you can't see the previous steps. So I'm sorry about that. I wish that I had access to a blackboard or a whiteboard, but slides are definitely the way to go if one's using Zoom. Are there any more questions about this? Again, you should think of a limit as being just, this approximation is increasingly good as the thing goes towards 0. Okay. So let's use the chain rule. Remember, the chain rule was if you take the derivative of g of f of x, you get the derivative of g evaluated at f of x times the derivative of f of x. Okay, so what's the derivative of this thing? Yeah, so in this particular case, we could take f of x to be x squared plus 1, and we could take g of x to be the cube of its input. So what you can do is you can take the derivative of a cube, which is 3 times the thing squared. That's just the derivative of g of x. Sorry, the derivative of g evaluated at f of x. That's this term here. Now, what about the term of derivative of f? Well, that's the derivative of x squared plus 1, which is just 2x, because this is 2x and this is 0. So it's 2x times 3 times x squared plus 1 squared. 6x times x squared plus 1 squared. Yep. It's important to remember to multiply by the 2x. Otherwise, I have done so many, like even knowing the chain rule, I have misapplied it so many times. Okay, what's the derivative of c of x? For c, a constant. Let's explore this question. Well, we can compute derivative of c of x is this thing. And let's just factor out c of x. So it's c of x times this. That's kind of cool. It means the derivative is going to look like some constant times c of x. C to the x. It's pretty cool for any c constant. So what is this constant? Now, this is where e comes in. And there are many definitions of the number e. Euler's constant. It is about 2.718. And it is the value of c for which this limit equals 1. This might be a little bit of a frustrating definition, but we will see how a lot of the other definitions of e, or all of the other definitions of e, follow from this one. So it's basically it is the particular value of c where the derivative of c, the derivative of c to the x, evaluated at 0 is 1. You have these plots of a curve that goes up for exponential growth. The slope evaluated at 0, e to the x is the particular curve where that slope is 1. Exactly. So in this case, then e to the x is just e to the x times 1. Sorry, the derivative of e to the x is just e to the x times 1. So the derivative of e to the x is just e to the x. This is, in some sense, the core property of e, that the derivative of e to the x is e to the x. We will see so many different applications of this, and you can find out lots more. There is a debate that's held periodically in I forget where, Williams College maybe, about e versus pi, which is the better number, which is cooler, e or pi. E turns up everywhere just like pi. I'm probably on e's side. But yeah, pi is also really cool. So more about e. You might have seen another definition, so let's quickly derive that. So we know that this equals 1. That means if we were to set n equal to 1 over h, we can write this as another kind of limit. So when, again, remember we can just like change limits around. So when h is going to 0, n is going to 1 over 0, so infinity. Okay, so let's write this as lim n going to infinity of just doing the substitution e to the 1 over n. H is equal to 1 over n. Minus 1 over 1 over n. Okay? So this is just the same thing, just rewritten with n equal to 1 over h. That means for n large, this is a good approximation. So for n large, we have e to the 1 over n minus 1 is about 1 over n. And if you rearrange this, you get another definition of e, which is the limit as n goes to infinity of 1 plus 1 over n to the n. So 1 plus 1 half squared, 1 plus 1 cubed, 1 plus 1 third cubed, 1 plus 1 quarter to the fourth, and so on. That sequence converges to e. You will eventually get very, very close to e. This is another definition of e that you might have seen. But it just follows from the one that we saw. Okay. Now we've seen derivatives of polynomials. We've seen derivatives of e to the x, and more generally, c to the x. What's the derivative of log x? And in general, in this course, we're going to be using log x to denote the logarithm base e. We are not in the natural log. We're not going to be using it to denote like log base 10 or base 2. Base 2 is reasonable. Base 10 is just sad because it's very like human-centric. We just happen to have 10 fingers. Log base e is sort of a mathematician's way of doing things. Log base 2 is sort of a complexity theorist's way of doing things. Okay, so that is log of e to the t is just equal to t. Great. So what is the derivative of log x? And why? Why is this true? Yes, it is equal to 1 over x. Why is that? How can we prove that? Just using the tools we have. Aha, so we can do what we did with the product rule before to work out 1 over x to the n. We can do this now with a chain rule. So suppose this derivative exists and it's f of x. Then we can apply the chain rule to get the derivative of log of e to the t. Now, log of e to the t is just going to be t. But we can apply the chain rule to it to work out that this is going to be the derivative of log. So f evaluated at e to the t times the derivative of e to the t, which we know is just e to the t. This is just the chain rule applied to log of e to the t, where again, f of x is our mysterious derivative of e to the t, of log. So we don't know what the derivative is. We assume it exists. So now what do we have here? Well, we have a formula for the derivative. But we know that what this derivative has to be is the derivative of t with respect to t. which is just 1. So 1 equals f of e to the t times e to the t. So f of e to the t is 1 over e to the t. And then, as the suggestion is in the comments, substitute x for e to the t. That means for any x, notably for any x greater than 0, but we only can do logs for x greater than 0 anyway. We have the derivative of log x is equal to f of x is equal to 1 over x. This is a question, do we need to prove that it exists? This is a really good point. We didn't prove that it exists, so this is not a full proof. This is assuming the derivative exists. What is it? Yes, that is correct, and it is a very good question. Okay. So, derivative of log x is 1 over x. This is another reason why e is important, because 1 over x is kind of an important function, and the thing that gives you 1 over x as its derivative is really important, and that's log base e of x. How would we go about proving that it exists? There are a bunch of different ways. I'm not going to go into it. I'm sorry. I didn't really go into like what makes a function differentiable. So yeah, I'm going to gloss over that. If you want to look at the derivative of a log base something else, use the base change formula and use that as a constant. And so you'll end up with the thing that you would have gotten for log base e times a constant. And yes, log of e to the t is t, but we were taking the derivative of that. So the derivative of t with respect to t is just 1. So exactly, yes. That's how we got this. This left-hand side is just the derivative of t, which is just 1. We were deliberately doing something, evaluating the derivative of something that we knew. We were just doing it in a way that allowed us to use the chain rule. And because we used the chain rule, we were able to work out some property of this unknown function f. And we were able to work out what f is actually from the chain rule. Is this enough to show that it holds for all x greater than 0? Yes, because any x greater than 0 can be represented as e to the something. Okay. Double derivatives. If we take the derivative of something twice, we're going to write it like this. Just double d over d by dx squared, as it were. The double derivative of a function can also be written as f double prime. As an example of what double derivatives are like, we can take the double derivative of x squared plus e to the x. If we take the derivative once, the first thing becomes 2x. The second is just stays at e to the x because derivative of e to the x is e to the x. And then when we take the derivative again, the e to the x again stays, and we get 2 plus e to the x. So what is a double derivative? It's measuring the rate of change. So the derivative is like the rate of change. It's the slope, the rate at which something is changing. It's measuring the rate of change of the rate of change. So for example, acceleration is a second derivative. It's the derivative of velocity, which is itself the derivative of position. Velocity is how fast your position is changing. Acceleration is how fast your velocity is changing. These are actually vector valued quantities in physics, but you can think of them as single variable quantities. So geometrically, this is measuring the curvature. And the curvature of this function is basically like how much the slope is changing. And negative curvature means the slope is getting smaller. It starts out positive and it's becoming negative. No curvature means the slope stays the same throughout. It's just a line. And positive curvature means the slope is increasing, so it's getting bigger. That's what these pictures look like. So if a function has its double derivative being greater than or equal to 0 for all x, we say it is convex. So the positive curvature case. That means that the slope is increasing, the derivative is increasing. We say it is convex. If a function has the double derivative less than 0 for all x, we say it is concave. So this looks like it's convex, and this looks like it's concave. It's important to remember that convex and concave are not opposites, in the sense that most functions are neither convex nor concave. Most functions have places where where the double derivative, the curvature, is positive, and also places where it's negative. There are different notions of concave and convex, but typically you would use this is not strictly greater than or strictly less than. It's greater than or equal to. Yes, if the function is linear, then it is both concave and convex. So they are neither opposites nor mutually exclusive. So I think that we will move on to Jensen's inequality next time, and we will then go on to prove AMGM, which we saw at the start of class. Sorry, there's a lot of stuff to cover. We will have plenty of time. I think I'm going to insert another class on more cool calculus stuff. Mostly things like Taylor series and why they're really awesome and super useful. And also looking at like the asymptotic behavior of different functions. But we will move onto that on Monday. Have a good weekend, everyone. And here is a poll for the speed of today's class. Okay, great. Thank you, everyone, for coming. Good luck with the problem set. I encourage everyone to post on Slack if you were looking for collaborators or if you have questions. Bye, everyone.